Okay, so now we've seen a kind of graphical or geometric, intuitive way to see and visualize the effect of length contraction. Let's now derive it using our Lorentz transformations. So if you'll recall what we did, I'll just sketch it briefly again. Just giving the positive quadrant. We said that we had some stationary observer A with coordinates x and ct, and then we had our boosted observer ct hat and x hat, and then we had some rod, or just some purely space-like interval that was at rest in these hatted coordinates in the B frame, which we now understand as being a frame which has been boosted relative to this A frame, i.e. a frame moving through the A frame with some coordinate velocity. And so this observer A is going to now see this rod moving through that frame, and the observer B just stays at rest relative to this rod. And so they can measure its so-called proper length, which I'm going to call, now I'm just going to call it L, so that's the length of the rod. Now what I did was use the quite convenient fact that on this diagram we could draw one of these parabolae of constant line element separation from the origin. So I could match up that this length L in the x hat coordinate would correspond to an x coordinate value, something like this. But then, as we know, the world line of this endpoint is really how it's appearing in the A frame, and the world line of the endpoint is going to be some parallel line to this t hat axis. And so just by looking at this figure, we can clearly see this is the length. Now I'm going to call delta x, which the observer A assigns to this rod, and we can already from this figure clearly see it's now just purely in the Euclidean way, because we're measuring a space distance. We do just use the plus dx squared part of the metric, and so all space distances are Euclidean distances. And so just the length of this rod, our Euclidean brains are allowed to associate its length with what we like to associate, and so we can clearly see that it's shorter than this rod as would be viewed by the stationary frame, and we can already quite rigorously or not rigorously, but quite clearly see that this would always have to be true just by looking at one of these hyperbolae. We know that this has to be the coordinate or correspond to a coordinate value of L. So whatever the actual coordinate value is going to have to be less than L. But now let's derive this using our Lorentz transformation. Okay, so to formalize this then with the Lorentz boost, what I'm going to want to do is take this currently unknown interval in the A stationary frame, which I'm just giving the name of x, or I could call this delta x, and then I'm going to boost into this B boosted frame and see how that interval appears. And I'm going to, well, I should know that it's going to have a length L in the boosted frame, and then using the form of the boost we can use that to work out what this currently unknown delta x is going to be. So what I'm going to be wanting to do is express my new coordinates, i.e. the boosted t hat coordinates, which are going to be given by our Lorentz boost matrix times our original coordinates. And so now what I can identify, what I'm trying to calculate is, I'm trying to work out how this unknown interval, or just point delta x, which lies on the t equals 0 axis, I'm looking at how that is going to be boosted into this B frame, which I know should correspond to this point up here, which is going to have coordinates Again, t hat is equal to 0 on this line, but this x hat coordinate is going to have to be equal to L. Okay, so I really only need to consider how the spatial coordinate of the endpoint of the rod is going to change. And so from this matrix multiplication, I can just see I'm going to get minus v over c gamma times 0, and then a plus gamma times delta x. So I can just see that this L is going to be gamma times this coordinate interval, delta x. And so now how we should understand this, well, first of all, it's convenient to remember that this gamma function kind of starts at 1, and then as the velocity increases, it blows up at around, or as v approaches this value c. So looking at now this expression, remembering that this L is the proper length as measured by the x hat frame, we can now realise that if this L, well, it's going to be fixed because it's fixed in the stationary hat frame, and so as this, or now as gamma is around 1, we can just see that this proper length is going to be the same as this coordinate length. But as now this gamma starts to massively increase as this velocity approaches c, in order to keep this L fixed, if this gamma starts increasing, then this coordinate interval is going to have to start decreasing. So if we view this rod now as seen, or we see the rod moving through our frame with a quite large velocity, and so its gamma is very large, we're going to measure, or the delta x is going to be the coordinate interval that we're going to measure and associate to the length of that rod. We're going to see it appears in our frame to be much shorter than it does as if we've been at rest with respect to that rod. And so now we should compare that to the fairly similar, but in some senses kind of slightly inverse time dilation formula, where we saw that essentially the time, the coordinate time, could be obtained from the proper time in a very similar looking way. But now we see that this is kind of an inverted form of this expression, if you like, because the fixed quantity, this proper time, is fixed. So maybe it might be better to write the fixed quantity and then write it in terms of the other quantities. So this is now going to be t over gamma. And so the left-hand side, this tau is going to be fixed. And so as, well, if gamma is just 1, then obviously coordinate and proper time are going to be the same. But now as this gamma starts massively increasing, we can see to keep tau fixed, this t is going to have to increase. And so this is time dilation as controlled by the gamma factor. And now this is length contraction as also controlled by the gamma factor. So this Lorentz factor is now really, really useful, and it gives a really good measure of essentially how relativistic the system is becoming, or how much of these, or how extreme these physical effects are going to start becoming, because gamma can essentially become infinitely large as you approach this velocity value of c. These lengths and times can potentially dilate all the way up to infinitely, and we're going to see that this in some sense is one of the reasons that you're prevented from ever going faster than the value of c, because if you're living in v less than c and you keep trying to boost to higher and higher velocities, so now as we see, as we approach but we never quite reach this v equals c effectively speed limit, this gamma factor just increases all the way up to infinity in our space and times, as if an observer were now moving us, trying to accelerate up to this speed v equals c, they would see us shrink down to an infinitely small point, and they would think that we're experiencing an infinitely large coordinate time, which is essentially one of the reasons why you can never start from below this speed v equals c and accelerate up to it, because essentially you're going to then have to be seen, or you would be then seen to take an infinite amount of time to achieve such a high value of gamma. So in summary then, we've done a fairly similar calculation to how we derived our time dilation, just by using a Lorentz boost to look at how an interval, or just a coordinate value in this case in one frame, is boosted to appear in another frame. And by considering the endpoint of the rod, we were able to derive, or first of all, we know that in the fixed stationary frame of the rod, it's going to have a fixed proper length, and then we were able to come up with now an expression that's going to relate the coordinate length of this rod that the observer A is going to measure. That's related to the proper length through this factor gamma, and as we've seen, as this gamma is going to become infinitely large, this is going to cause this coordinate length to decrease from this proper length, which is known as the phenomenon of length contraction, and colloquially we can sometimes state this as the moving rods are shortened. And basically, if you see any object now moving through your reference frame, if you're stationary and you watch an object fly past you, not only are you going to see that object moving through your frame with some velocity, it's going to shrink as it moves through your frame. And you're also, not only are you going to be measuring the wrong spatial size of this object, you're also going to be measuring the wrong amount of time at which this object is elapsing. The actual time which is elapsed is, from the particle or the object's perspective, is going to be much shorter than the actual time at which you measured to have elapsed. And so these are the two phenomena of length contraction and time dilation. And so now we can really clearly see why these now coordinates, we essentially can't use them to describe any, or they're now essentially really tied to observers, and we can't use them to describe, or say, parameterize a world line, because, well, this coordinate is going to be different for everybody that moves at a different relative velocity, and because we know that all of these observers moving at different relative velocities are all just different coordinates that are connected by Lorentz transformations, we can basically realize that these coordinates are not a good way or a good measure to define sort of invariant quantities like parameterizations of curves, because, well, basically everybody's going to disagree on what the values they would be assigning to their parameterized curves. But now the only kind of nice or good quantities that we have access to are these proper times and lengths, because we can measure these in a fixed reference frame, and their values are then fixed by the invariance of the metric tensor. We can then always use these proper times and lengths. They're kind of, if you like, accessible by all observers. And then using these kind of formulae, we can then match up all of these different observers' coordinates just by knowing that they're related by this gamma factor, which is kind of controlled by how fast these coordinates are moving relative to each other. So we always just need to kind of now think in terms of proper times and distances, and just realize that these coordinates are kind of slightly fictitious, or they're not the proper assignments of the actual fundamental time and distances of what we would like to associate with whatever object we're describing, and the kind of artifact of how these coordinates are going to change is a kind of, well, it's due to the relative velocity that you are moving with respect to, say, the object that you're trying to describe. And so we need to just free ourselves from thinking about coordinate values as having meaning. What is the only real meaningful quantities are now quantities which we've derived using a metric, or that are somehow invariant quantities. And so we can only think in terms of these invariant quantities, and we need to remember that the coordinates are then going to be somehow related to how that quantity appears at rest in some coordinate frame. And so if you like, these stationary frames are, if you like, the most distinguished frames, because they are the frames in which we're allowed to assign these proper times and distances. But then these so-called inertially moving reference frames are also still valid. They can equally well describe these, if we say that we would associate proper times and distances with physical quantities now, so actual physical lengths of objects and the physical time a particle would experience, we can still transform and work freely in an inertially moving reference frame, still understand all of these fundamental physical properties. We just need to always remember to adjust essentially the coordinates based on how fast we're moving relative to that fundamental physical quantity. And if we're just not moving relative to that physical quantity, we can just use our coordinates to freely measure it. But then if we start transforming those coordinates, we just need to compensate in this simple, or fairly simple way. But now all the physical effects we can just now realize as being simply just an artifact of how you're measuring the space-time. They're kind of not really actually fundamentally physical, they're just kind of side effects of the coordinates that you're using. The length isn't actually physically stretching or contracting, because if you're just at rest with respect to the rod, nothing happens to the rod physically. The interatomic separations of the rod aren't changing, but how you would view that rod now as now just a mere observer, which is someone who's just assigning coordinate values to the positions where they saw the rod in their frame. This is a kind of weaker notion than the actual fundamental physical proper length. The proper length is never changing, it's just the kind of arbitrary values that an observer is assigning to that proper length. And these are now affected by the observer's motion relative to this fundamental proper length.